Okay, welcome to the new chapter. We've looked already at how you can predict what kind of reactions will happen if you have a redox system. You'll have an oxidizing agent, you'll have a reducing agent, and they'll exchange electrons. Now we're going to get more concretely into what would one of these reactions look like if you set it up? What kind of containers and wires and things would you need to connect in order to make the reaction go? And that setup is not all that different each time. It's pretty consistent, but let's go through an example from start to finish. What they're asking here is they give us some chemicals and they say, given these things, identify where the cathode and anode would be, where the oxidizing agent, reducing agent would be, and which way electrons and ions would flow if you set up this cell. So before we can do any of that, we have to do some things from the previous chapter where we just say, given all these chemicals, what reaction are we going to get? And they tell us we have an acidified solution, which means we have H+. This is the procedure we used to do where we would get all of our cast of characters, all of our available species in a list, and then we'll find our oxidizer and reducer from that. We have potassium dichromate, which means we have K plus and Cr2O7. We have an iron electrode, so a solid lump of iron, and a solution of iron 2 sulfate. So we have iron 2 ions and sulfate ions. So let's get a redox table and see what's going to happen here. Okay, so as we've done before, we will read down the left side of our redox table to find our strongest oxidizer, and then we'll read up the right-hand side to find our strongest reducer. Going down the left side, fluorine we don't have, lead oxide we don't have, acid permanganate we do not have, gold perchlorate, chlorine, and soon enough we get to this line. This will be our strongest oxidizer, the acid dichromate. We have acid because they said was an acidified solution, and we have dichromate ions, so this reaction can go and it'll produce chromium-3 and some water for us. Then we read up the right-hand side, and happily, the strongest reducer is just barely at the bottom of what you can see here. It's the iron. The iron metal in that bar will react. It turns out the iron sulfate isn't contributing much of anything, but that reaction can take place. We can go from iron to iron 2. So good. Let's flip back to here and get our two reactions down. So we are going to have, just copying out of the data book now, Cr2O7 plus 14 hydrogen and 6 electrons. And that produces 2 chrome 3s and 7 water. That is our strongest oxidizer. On the other side, our strongest reducer is just iron metal, this, which will convert to iron 2 by giving up 2 electrons. I want to combine these, which I cannot do right now because their numbers of electrons do not match. This one's talking about 6 electrons and this one only 2. So we can fix that by tripling the entire iron reaction. We'll say 3 times as much of this, 3 times as much of this, and 3 times as many electrons gets us to 6. Now that those match, we can add them together. The electrons are spectators, so we can stop caring about them. And our net reaction, or our overall cell reaction, will be Cr2O7 2 minus, 14 hydrogen ions, 3 iron atoms, turning into 2 chrome 3 ions, 7 water molecules, and 3 iron 2 ions. Okay, so that's our overall reaction. We already found that the hydrogen and the dichromate together, working as a team, are our strongest oxidizing agent, and that the iron metal is our strongest reducing agent. So there's two of our items taken care of. Now, what is it going to look like if we actually build this cell? I'll shorten that up a little bit. Whenever you're building a cell like this, you're going to have two glass containers. They don't have to be glass, but they generally are, so we can see what's happening. You pour water into them. So here's the water line in each of those. You have to have an electrode, a solid bar of some kind on either side where the reaction can occur. And in this one, they said one of the electrodes is iron. So this is a bar of iron metal. On the other side, they said there was a carbon electrode, as in graphite. It would look kind of like a stick of pencil lead. Carbon is inert. It does not react with much of anything. It is not to be found on our redox table, and that is why I didn't put it in our list of chemicals up here. I'm sorry, I meant to bring that up earlier. But anytime you see an electrode made of carbon or platinum, you can assume that that will not react. That's the reason they're used. They'll sit there and they'll conduct electricity, and chemistry can happen on the surface of a carbon electrode, but the carbon itself will not participate. Now, you need an electrical connection between these two sides, and so you connect a wire between the carbon and the iron electrodes. There would probably be an alligator clip on either end of this wire. You clip that onto the carbon, and over here you clip it onto the iron. Or you could just wrap the wire around the electrode. It doesn't really matter as long as there's a good electrical connection there. And the last piece we need, because the electric charge wants to flow in a circuit going all the way around, we need a way for the water to be connected between the two beakers. And what we use to connect them is a thing called a salt bridge. A salt bridge is something that ions can pass through, and it's essentially a flexible piece of tubing, usually plastic. Inside it is agar gel, generally. It's like unflavored jello with salt mixed into it. And the fact that it's got salt mixed into it means it's full of ions. They can be sodium and chloride, or really any ions will do as long as they're able to move. And the fact that there's positive and negative ions in here means that electric charge can be conducted through this salt bridge. And then to keep all the contents from leaking out, you stuff the ends with cotton balls or some kind of plug that will hold the gel solution in there. And that means if you're an ion, positive or negative, you can move through the water, through the gel in the salt bridge, and get from one side to the other. So the salt bridge completes an electrical circuit and allows this whole thing to work. Okay, so how do we label all of our pieces here? We have on one side of this, they said the carbon electrode was in a potassium dichromate solution. So we have potassium over here. We have Cr2O7 over here. We have iron 2 on the other side. We have sulfates on the other side. So there's what our cell looks like before anything happens. And now what's going to happen is we have one reaction where the dichromates and the acid are going to produce chromium ions and water. That's the reaction on this side. So on this side, we're going to be using up potassium dichromates, and we're going to be making chromium ions. Now, if you check in your data book on the ion color list, I believe you'll find that chromium ions, what are we making here? Chromium 3 ions are blue-green when there's a lot of them, or more like green if there's only a few. So around this electrode, where we're creating chromium ions, you can expect to see a blue-green color forming. It's going to look like the electrode is sweating blue-green because chromium ions are forming right on it. They'll appear on the surface, and after that they'll start to disperse out into the water. So you'll get a green color spreading out into the solution from this side as chromium ions form. Over on the other side, in this beaker, solid iron is going to get used up and turned into iron 2 ions. So on this side, for one thing, we will see that the iron electrode, the solid iron here, is going to start getting eaten away. This electrode's going to lose mass. The surface will start to look a little pitted at first, and then it'll actually start to crumble and come apart as solid iron is used up. And as that happens, iron 2 will start to appear in your solution. Iron 2, according to our table, is lime green. So on this side, you'll start seeing a different green color appearing around this electrode, and then that will start to disperse into the solution as well. So we'll have blue-green appearing over here and lime-green forming on this side. Which way, let's see, let's get, all of that is interesting, but it doesn't cover any of the questions here, so let's knock some of these off. They say find the cathode and the anode. My trick for remembering these is that reduction and cathode both have a C in them, and oxidation and anode both have an A in them. So wherever your oxidation reaction is, that side is the anode. Wherever your reduction is happening, that side is the cathode. This reaction, where we're gaining electrons, Leo says gaining electrons is reduction. This reaction is reduction. So the side where it's happening over here is our cathode. And over on the other side, this is iron losing electrons. According to Leo, losing electrons is oxidation. Oxidation must be the anode. So this iron bar is what we would call our anode. These two solid pieces are both called electrodes, and the more specific names are one of them is the cathode and one is the anode. So we've got that covered. Good. Okay, so cathode and anode done, oxidizing agent and reduction done. Direction of electron flow. This reaction, the chromium reaction, is using electrons. It's saying, give me electrons and I will do my thing. So there must be electrons flowing into the chromium side. And in this reaction, we have iron turning into iron 2 and releasing electrons. So this is the reaction where the electrons are coming from. They appear on this side and then they flow up through the wire. So all that is consistent. The electrons will be flowing from right to left through the wire. You can memorize, if you want, that the electrons always flow out of the anode and into the cathode. I never like that. I prefer to work this out every time just because the rule is not all that difficult. You just get it out of these reactions. This reaction says, I consume electrons. This reaction says, I produce electrons. So this side produces electrons and pumps them over towards the left side. Now, which way will electrons flow? This is easy once you have the electron. Or sorry, which way will ions flow is the question here. And I find that's easy to work out once you have the electrons figured out. Electrons are negative. Electrons will flow in this direction. So here we have E minus flowing like so. As negative charge flows into this electrode, any negative ions down here are going to want to flow in the same direction. So any negative ions you see will tend to circulate this way. Negative electrons going that way counterclockwise. Any other negative ions will want to flow this way through the circuit. And positive ions will tend to flow the other way. So we will have iron 2 will start to, not only will it come out of the anode and start to fill up this beaker, as this beaker turns green, eventually iron ions will start to flow up through the salt bridge, and the salt bridge will start to turn green as it fills up with iron ions. If you run this long enough, they will even make their way out the other side, and you'll start to get iron in the left side of the beaker. So the general rule is whichever way the electrons are flowing, negative ions will flow the same way, in this case counterclockwise, and positive ions will tend to flow the other way, clockwise. All right, let's see if we can do that again. We'll go a little quicker on this one so this doesn't become an insanely long video. All right, platinum electrode, that's inert, so I'm going to ignore it. It's not going to react. I'm glad it's there. The system needs it, but it's not going to contribute. We have hydrogen gas, hydrogen ions, a zinc electrode, that's zinc metal, and zinc ions. There's only one form of those, and it's zinc 2. So if we go to our redox table and start reading down the left side, we get our fluorine and our lead and our acid permanganate and our acid dichromate and all that. There's a lot of reactions that have H plus but also require something else, so those don't help us. And eventually, right in the middle of the page, we get the hydrogen reaction. 2H plus 2 electrons produces hydrogen gas. And reading up the other side, about a quarter of the way up, we get zinc. I'm writing this one opposite the way it looks in the book because it's the reduction reaction. Or sorry, it's the reducing agent, so it's the oxidation reaction. My bad. So that will be zinc converting into zinc 2 and 2 electrons. Happily, the electrons match already, so it's easy to condense this and say that we've got 2H plus zinc turning into elemental hydrogen and zinc ions. So that's the overall reaction in this cell. How will it look if we hook it up? Well, let's see. Lock that. They said we had a platinum electrode over here. And in this solution we have hydrogen in gas form and hydrogen in ion form. So the hydrogen in gas form would be just like when you bubble oxygen through an aquarium to get oxygen into the water. You can bubble hydrogen through water and some of it will dissolve. At that point you can't see it anymore, but it's still present mixed in with the water molecules, and that's a solution of hydrogen gas. And over on this side we have zinc metal for this electrode, and we have a solution of zinc ions. Zinc ions, sadly, are colorless, so we won't see anything in this solution. This will look like water when we first see it, and I believe this side will too, unless it's so loaded with hydrogen that it's actually bubbling like pop, but that wouldn't necessarily happen. You can have a hydrogen solution that just looks like ordinary water, so nothing much going on in this when it's first set up. Now, in the process of making these reactions, we decided that hydrogen ions are our strongest oxidizing agent. They were the highest thing on the left side. And zinc metal was our strongest reducing agent. It was the first thing we found reading up the right side. So we've got our oxidizing and reducing agents. That's fine. The reaction on this side will be 2H plus producing hydrogen. That reaction is this oxidation or reduction? We're gaining electrons, so that says it's reduction. The other thing you could say is because we have hydrogen in +1 form here and it's 0 over here, that's another way we could determine that this is reduction. So this side is where the reduction reaction is happening. And reduction has a C in it, so this side must be the cathode. That means this must be the anode. Or you could say zinc is being oxidized. Oxidation has an A in it. This side must be the anode. Okay. So remember here, I'm not talking reducing agent. I'm saying the reduction reaction is on this side. That goes along with the cathode. So cathode and anode, done. Direction of electron flow. Which of these reactions consumes electrons and which reaction produces them? This reaction is zinc spits out electrons, so the zinc is giving out electrons. And so electrons, it stands to reason, would flow this way. And that way. And over on this side, the hydrogen reaction does consume electrons, so it makes sense that they would keep flowing in there. And the H pluses would be saying, yes, good, electrons, keep them coming. We want to combine with those and turn into hydrogen gas. So electrons will flow that way. Negative ions would flow in this direction, but they didn't mention any. So if only there were negative electrons, they would flow this way through the salt bridge and counterclockwise, but it seems that none of that will be happening. Positive ions will flow in the opposite direction. So while negatives, sorry, I don't want to say electrons, while any negative ions that would flow counterclockwise through the circuit, any positive ions that we have, like say zinc, will flow clockwise. They'll come off the zinc bar, flow out into the solution. Soon enough, they'll find their way into the salt bridge and traverse the salt bridge and flow this way. And over on this side, we even see that the hydrogen ions are going to be flowing towards the cathode because they want to react. Right on the surface of the cathode is where a hydrogen ion can meet electrons, which will conduct down through the bar, and right on the surface they can meet and turn into hydrogen gas. So, this isn't part of the question, but let's cover it anyway because it is important. How will you know when this reaction's happening? H pluses will disappear, which means this solution will become less acidic as time passes. At first, the solution will have a low pH because it's loaded with hydrogen ions, but the pH will start to creep up towards 7 as these hydrogens are used up. Also on this side, hydrogen will form on the surface of the electrode, which means you should see bubbles. They'll appear, at first they might just stick to the surface of the electrode if this reaction isn't going very fast, but if there are a lot of bubbles, they'll start to form on the surface and then float upwards. When they get big enough, they'll break free from the electrode surface, fizz up to the top, and the top of this will start to foam as hydrogen gas forms. If you wanted, you could take a cup, turn it upside down, and trap the hydrogen with it, and get yourself a cup of hydrogen. Over on this side, zinc metal is being consumed, so this electrode will start to get eaten away. It'll start to lose mass. It'll eventually crumble down to nothing if we consume all the zinc metal, but at first the surface will go from smooth to pitted, and then pieces will actually start to crumble and fall off eventually as zinc reacts and dissolves into the solution. It'll be like the solution is corroding or eating away at the zinc. What's really happening is zinc atoms are jumping out into the solution and floating away. All right. Here's another one, same question. Let's see. Let's get efficient here. We have copper in a copper 2 solution, nickel electrode in a nickel 2 solution, so all that is nice and simple. Technically there's water in here. I should be mentioning that even though it hasn't been an issue in the last couple reactions. Stay alert to the fact that water can react in a cell, and sometimes you don't want it to react, but it can anyway. So if we go to our redox table and read down the left side and up the right side to find our agents, copper 2 turns out to be our strongest oxidizer, and nickel metal turns out to be our strongest reducer. So the two reactions we get are copper 2 plus 2 electrons produces copper, and on the other side, nickel turns into nickel 2 and releases 2 electrons. The electrons we can kind of forget about because what we really care about is the chemical reactions here. What does that look like when you hook it up? Well, on one side we have copper metal and copper ions. On the other side, we have nickel metal, a bar of nickel in a solution of nickel ions. We found that copper 2, the ions, are our oxidizing agent, and nickel metal is our reducing agent, so that part's covered. Where is our oxidation reaction and where is our reduction out of these two reactions? This is copper 2 gaining electrons to become copper. Gaining electrons is reduction, according to Leo Szesger, and so reduction has a C in it. That happens at the cathode. So that's from gaining electrons is reduction. So the reduction reaction is happening on this side, and reduction has a C in it, which means this side is the cathode. I hope that makes sense. If that doesn't make sense, I hope you have some other system for finding cathode and anode. I think this one's reasonably simple, but it's not the only way, of course. Over on the nickel side, we have nickel losing electrons. According to Leo, losing electrons is oxidation. Oxidation has an A in it, so this side is the anode. Anode. Okay, got that, got that. Which way do electrons flow? We have this nickel reaction producing electrons, so they must flow that way. And if negative electrons are going counterclockwise here, any negative ions would be flowing counterclockwise through the bridge like this. Thing is, they didn't tell us about any. They said a copper 2 solution, but they didn't say it was copper chloride or copper nitrate or whatever, so if there were negative ions, they would flow in this direction. Positive ions flow the opposite way, and so we get, it makes sense that we get nickel coming off of the nickel bar into solution and then flowing clockwise. So nickel will go in that direction, and copper will also go clockwise because it's attaching itself to the copper bar. Copper 2 is combining with electrons and turning into solid copper. That means over here on the cathode, we're actually going to get new copper metal forming, and this electrode is going to get bigger. When this happens, we say that copper is plating onto the copper electrode or onto the cathode. Anytime something is gold plated or silver plated, they did it like this. They took ions and had them attach onto the metal using electrical current. And so we say that the metal is plating because of that. This is copper plating onto our copper cathode. So this will start getting bigger as the reaction goes, as more and more copper builds up. Over on the other side, the nickel bar will start to get eaten away because it's dissolving. Nickel metal is turning into nickel ions, so you'll lose mass. And that'll start to get eaten away. And last thing we could do if we're interested in evidence for this reaction, if you look on your ion colors, nickel ions, nickel 2 ions, they say are blue-green. So over on this side, as nickel atoms dissolve into solution, this right beaker will start to get a blue-green color to it. And that blue-green will spread out into the solution, and eventually blue-green will even start to spread out through the salt bridge and move towards the left-hand side. That color will get stronger and stronger as you produce more and more nickel. Copper 2, on the other hand, is a very pretty blue color. And originally this solution would be full of blue because of the copper ions. That blue color will fade as copper ions are used up. As they turn into shiny orange copper metal, the blue color will disappear. So on the right side, we get blue-green getting stronger, and on the right side, we get blue color fading. If it fades away completely, if we run out of copper ions, then the reaction will stop because there's no more copper to keep the reaction going. Okay, last one of these. Carbon electrode. Carbon, like platinum, is inert, and so we're not going to include it in our list of chemicals. We know it won't do anything. So the list of interesting chemicals starts with acid permanganate, H plus, MnO4 minus, and a lead electrode in lead 2, and I don't think the sulfates will do anything, but we'll keep them on the list. And technically we have water also because they said solutions, so I suppose that might do something, but I'm betting against it. And if you start reading down the redox table, let's clear away this stuff from the previous example. Acid permanganate is the third one on the list. It's one of the very strongest oxidizers, so that'll definitely be our SOA. And for the reducer, oh, look, okay. Well, chemistry has decided to punish me for my complacency, saying that the sulfate wouldn't do anything. The sulfate's doing something. Lead and sulfate together are our strongest reducing agent. I was thinking we'd hit the lead up here, but nope. Lead and sulfate together are the SRA. Okay. Chastened, I will go back here and write out my reactions. So we have the acid permanganate, MnO4, and 8 hydrogen, and 5 electrons. Converts to manganese 2 and 4 water. And on the other direction we have lead and sulfate. Converts to solid lead sulfate and 2 electrons. So what's happening here is the lead is turning into lead 2, but then they're saying if there are sulfates present, the lead ions will quickly react with those and produce a lead sulfate precipitate. Now, if we were to combine these, we'd need the number of electrons to match, and that would mean doubling the entire acid permanganate reaction to get to 10 electrons, and multiplying this entire bottom one by 5, quintupling it. So let's get that done. Twice as much. Twice as much is 16. Twice as much here is 10 electrons. Twice as much, and twice as much there makes 8 water. And for this one, we have 5 times full works, and now our number of electrons matches, which is what we hope to see. So we've got our oxidizing agent. That would be the hydrogen ions and the permanganate together. And our reducing agent is the lead and the sulfate, the lead metal and the sulfate. So we've got those identified. Now let's get a cell up here and figure out what this thing's going to look like. So we are told on one side we have a carbon or graphite electrode in the acid permanganate solution. So over here we have H plus and MnO4 minus. And on the other side we have a stick of lead, or a bar of lead, in a solution of lead ions and sulfate ions. Okay, so they want the cathode and the anode. To figure those out, we need to identify where our oxidation is and where our reduction is. This reaction is gaining electrons because they're one of the reagents, they're reactants, they're one of the things you have to add to make this reaction go. So gaining electrons is reduction. So the reduction reaction is happening on this side, and reduction has a C in it, which is for cathode. So the carbon electrode is our cathode where the reduction is happening. Just by elimination, this side has to be the anode, but let's go through the drill just to make sure. On this side, we have a reaction that's losing electrons, giving them up, and that, according to Leo, losing electrons is oxidation. oxidation has an A in it, and that tells us this side is the anode. There's always one anode and one cathode, so really once you have one of them, you instantly know what the other electrode must be. But it's good to be able to find it either way. Okay, so we got cathode and anode. We found our OA and our RA. Now, which way are electrons going? This lead reaction is releasing electrons, and so electrons would fill up the lead bar, and then because they all have negative charges, they repel each other. So all the electrons are thinking, let's get out of here. Let's go somewhere where it isn't so crowded with negative charge, because we are repelled by negative charge. And so the electrons migrate over from right to left. You can say the electrons are going counterclockwise. You can say they're going right to left through the wire. Either of those is okay. And over here, it makes sense that electrons would come flowing in because there's a reaction here that's eating up electrons. And so electrons come rushing in here because if they do, they can combine with hydrogen and manganese and participate in this other reaction. So if negative electrons are flowing counterclockwise, down here, any negative ions that we have, like the permanganate, should also flow counterclockwise. Permanganate will want to flow up into the salt bridge. That's not great because this reaction needs permanganate. It's going to start escaping in this direction, and so that might be a problem for this reaction if you try to keep it going for a while, is that your permanganate starts leaving on you. But it will try to migrate in this direction because all the negatives are flowing counterclockwise. And at the same time, positive ions, such as lead, will want to flow out clockwise through the solution. And the same with hydrogen. Hydrogen will want to go clockwise, meaning it will be attracted towards the bar here. And as for evidence that this reaction is proceeding, the lead electrode should start to dissolve because lead metal is being consumed. We'll see that. Lead sulfate, if it forms as a solid, will accumulate in a little heap at the bottom of the beaker. I believe lead sulfate is colorless, or that lead ions are colorless, so this probably would be like a white grains. So a colorless solution with a colorless precipitate appearing at the bottom. And there is a color for manganese ions and for permanganate. Permanganate, MnO4, is purple, and manganese, this, is pink. So over on this side, if you have this acid permanganate solution, this will start out looking like grape juice. It'll be purple colored. As the reaction goes, the purple color will fade, and you'll see a pink color coming off of the electrode as more manganese ions form. So on the left, we would see all kinds of colors, purple fading and pink getting stronger. And on the other side, because lead and sulfate ions are colorless, this solution would just look like water, and the only evidence of a reaction would be the dissolving electrode and a colorless, probably white precipitate appearing at the bottom.